Okay, so now let's move on to spontaneity of redox reduction. When we say a spontaneity, that means it occurs without any external forces or external influences. So the reaction is spontaneous if it occurs automatically by itself. So here we have a new equation and a new term. We have delta G. Delta G here is known as the Gibbs free energy. That's why it's G Gibbs. So Gibbs free energy is basically a unit. The unit for Gibbs free energy is energy. So it's a quantity of energy. So it describes, well, basically the energy, the changes in the free energy released or absorbed from the environment by a certain reaction. And here you see, you have N, and here is your the number of moles of electrons, and F is a constant. It's called the Faraday's constant. And then your E cell is the EMF, electromotive force, or your cell potential. Now, we have also a standard version of this one, the standard Gibbs free energy. How do you know it's a standard? If you have a 0 superscript. So that means it's a standard conditions. So N is the number of moles of electrons, F is your Faraday's constant, and the value of that is 96,500 joules per moles. So it's a constant of proportionality. So this is also equal to 96,500 coulombs, not calories. It's C coulombs per mole. So we have another equation here. Delta G is equal to negative RT ln of K. R is our gas constant. T is our temperature, and K here is the equilibrium constant. Now, there's another term, equilibrium constant. What's an equilibrium constant? It's basically the ratio between the products and the reactants in a certain reaction when that reaction is at equilibrium. So what do you mean by equilibrium? An equilibrium is a state where the rate of the forward reaction is equal to the rate of the backward reaction. So that doesn't mean that the reaction has stopped. The reaction continues going on. So there are reactants becoming products and the reverse, products becoming reactants. So basically this explains a reaction whereas you have a reversible reaction and the rate of the formation of the product is equal to the rate of the formation of the reactants. Now, take note that the one that must be equal here is the rate, not the concentration. So that doesn't mean that the concentration must be equal. It's just that the rates of conversion moving both sides must be equal. So let's say, for example, for instance, you have what could be a good example of a system at equilibrium? So let's say a system at equilibrium, you have your let's say people boarding the train. So people boarding the train. So for example, at Central Terminal, the one closest to Mapua. So Central Terminal. So in the platform, for example, you have 50 people in the platform. So 50 people in the platform waiting to board the train. Now, when the train comes, of course, there are more people inside the train than there are people outside the train. Now, the doors open, and of course, people will go out of the train, and people will board the train after. Now, the system will be called at equilibrium if the number of people that boarded the train that went is, say, for example, out of the 50 people that are in the platform, let's say only half boarded the train. So half, let's say for example, the train is packed or crowded. So inside the train, only 25 people went out. So that means only 25 people can get in. So the number of people that boarded the train is equal to the number of people that got off the train at that station. So we can say that is at equilibrium because the number of people boarding is equal to the number of people leaving the train. That doesn't mean that the number of people in the platform must be the same as the number of people inside the train. So that only means that the movement, the number of people moving in both directions are equal. So basically that's an equilibrium. So these are a lot of equations as you can see here, but and then cancellations. But I just want you to remember this triangle. So this triangle is shows the relationship between the cell potential, the Gibbs free energy. So your cell potential, the Gibbs free energy, and the equilibrium constant. So we can calculate one. For example, we can find out the standard cell potential from the equilibrium constant, or the equilibrium constant from the cell potential. The same goes from the delta G, the standard Gibbs free energy, from the equilibrium constant, or vice versa. So, and these are the equations that we can use to calculate one to get the other. So, for example, delta G and E cell, the equation here is delta G is equal to NF E cell. So, basically, this is this one. So, to calculate, for example, delta G given a cell potential, we just use this equation. Or to get the cell potential given a Gibbs free energy, we just use this equation. So, the same goes for this one. So, if we want to know the equilibrium constant, we are given the delta G. We can use this equation, negative RT ln of K. Or if we are given the equilibrium constant, or even the equation, the concentration at equilibrium, we can get the equilibrium constant from the concentrations of each of the reaction in equilibrium. You will see later. We can calculate Gibbs free energy. We can calculate Gibbs free energy. So this is the equation for calculating Gibbs free energy and the equilibrium constant. Now the other one here is from E cell to K. So getting K, for example, getting the value of K, equilibrium constant, from E cell, this is your equation. So you have basically, in here you just need to actually take note of these three equations to calculate one from the other. Sorry for these sounds. Okay, now, so how does it calculate to spontaneity? Spontaneity, we have here your delta G. So a spontaneous reaction is that you will know if the reaction is spontaneous if you look at delta G. So do not look at K or E. Do not look at K or E. Just look at delta G. If delta G is negative, you are sure that that reaction is always most likely spontaneous. If it's positive, that is a non-spontaneous reaction. So only delta G, look only at delta G to know if a certain reaction is spontaneous or not. Now, what is this determinants of positive and negative E potential? So as what we discussed a while ago, so positive E potential, that means it's the reaction is most likely will be spontaneous. A negative is a non-spontaneous E cell. So that reaction, as I told you, if you have a negative E cell, you got the reaction, you got the reducing agent and the oxidizing agent backwards. So you got the wrong the one that should be oxidized is placed as a the one that should be oxidized is placed as the oxidizing agent, and vice versa. So anyway, basically you got your E cathode minus E anode backwards if you have a negative E cell. So that is also related to a positive delta G. So this one is for delta G and E cell, you can see that if its E cell is negative, delta G is always positive. So that is a non-spontaneous reaction. Now for the K is a bit of a tricky thing to consider, because here K is just the ratio between the products and the reactants. So if it's greater than 1, so you have more products than reactants. If it's less than 1, you have more reactants than the products. If it's equal, they are the same concentration. So basically, this just gives us the concentration of the reactants and the products. As I told you in the train analogy, that doesn't really tell us if that reaction is spontaneous or not. Because what we are really obsessed, or what's really important here is the rate of forward and the rate of backward. So we are, rather than look at K to get spontaneity, look at delta G. So if delta G is negative, it's spontaneous. If delta G is positive, it's non-spontaneous. Now what if it's 0? Again, non-spontaneous. So basically, let's see this example. So what's the equilibrium constant for the reaction at 25 degrees Celsius? So here is, we are looking for equilibrium constant K. This reaction occurs at 25 degrees Celsius. So we can use here the equation. We have equilibrium constant here. We are given the reaction, so either we get the E cell or we get the Gibbs free energy. Now Gibbs free energy is we do not have a table of values for Gibbs free energy, but we have a table of values for cell potential. So we can use this equation. So from the table, the standard reduction potential table, we can calculate your E cell. So the E cell of stannum, that is tin and copper. So in here, your tin is the one that's being oxidized, and this is the one being reduced. So the anode is the tin, and the copper is the copper is your cathode. So if you look at our table, so I'll just exit it for a bit to go to our table a while ago. So if you look at the table here, so where is tin and where is copper? So here is your this is tin, so plus 13, and this where is copper? Copper. Tin and copper. So plus 15 and plus 13. So here your reducing agent is your tin and your oxidizing agent is copper. So the cathode is copper and the anode is tin. So 0.15 minus 0.13. So that is basically EO. So if you go back here, so let's see. Okay, so 0.15 minus 0.13. So basically this is your E cell potential. So calculated for you. Now your E cell must be equal to, this is what is this 0.257 volts per mole. So that's this one is from this value. Let me see. So again, this is NFE cell. So this is calculated. So they just from E cell is RTNF. So they just, since R is a constant, F is also a constant, and the temperature is usually at 25 degrees Celsius or 298 K. So all of these R, T, and F are constants. So they just calculated it as 0.0257 volts per mole. But I do not want you to use this value because it doesn't tell us much or anything. So I'd rather that you always use R, T, and F. So just input individual values of your R. By the way, the gas constant here is 8.314 joules per Kelvin mole. Not that the other one, 0.0821. Do not use 0.0821. Use the value of 8.314 joules per Kelvin. You have that in your calculator. The value for the temperature in Kelvin, and this is your Faraday's constant. But here you are given a shortcut, so they just used 0.257 volts per mole. And here is the moles of electrons. So then the movement of the electron, we have 2 plus, so you are moving to electrons here. So you have here the standard reduction potential. So 0.15 minus this is 0.14 ba yung nandun? So this is the given for the tin. So you have 0.29 volts. So tin, tama ba tayo ng tin? I think I look at the wrong tin. SN2 plus SN. So let's double check. So SN2 plus, where is it? Okay, SN. This one is SN4 plus. So we're looking for SN to SN2 plus. This one, negative 0.14. Okay, so I look at the wrong. So be careful on looking at that values. So tin, you have several oxidation or reduction equations in the table. So be careful of using the correct reduction in the table. So where are we? Okay, so here you have your E cathode minus E anode. So 0.15 minus negative 0.14. So you have a positive 0.29. So you basically have we can just look for ln of K. So the value 22.6 was not visible, but anyway, your value should be 7 times 10 to the 9. So basically, you are just going to substitute it to your equation and look for K. So basically, this is just simple as substitution. So your equilibrium constant has basically no units. No units required for equilibrium constant. So let's have another example. Standard free energy change for a certain reaction. So instead here of finding equilibrium constant, we have your standard free energy change. So again, instead of K, we are given your E cell. So we just gonna use your delta G is equal to negative NF E cell. So that is the reaction that gives to the energy and the E cell reaction. So again, look at the E cell from the table, identify which is the cathode and which is the anode, and then calculate. So E cathode minus E anode, you will get negative 4.37. The values here comes from the table that I showed you a while ago. Now that we have E cell, we just substitute it in the equation. So N is the number of electrons. So if you go back, how many electrons are moving? So Au to Au3 plus, that's 3 electrons, but you have 2 gold, so you have 6 electrons. Calcium 2 plus, 3 calcium 2 plus, you have again 6 electrons. So N is 6. F is the Faraday's constant, 96,500, and your E cell is the one we calculated a while ago. So just substitute everything in your equation, you get 2.53. So here, the key here is just how you substitute it for the equation, or rather, how do you choose the equation that you will be using, and you need to correctly identify your cathode and your anode. So anyway, that's it for spontaneity. So we will be looking at Nernst equation the next video.